So yeah, if you guys have any questions about entropy or Hess's law or anything like that, just let me know. Yeah, we can go over any problems on Hess's law or any entropy questions or heat equation questions or anything like that. There won't be a quiz tomorrow. Tomorrow is just the last day of notes. That's pretty much it. There's no assignment tomorrow either. I'm not sure who you are from your name, but yeah, that's still kind of up in the air. We're still trying to figure that out. I'm gonna have a department meeting tomorrow, so I'll see if I can ask them and see if I can get some more information about it, because I'm not sure how we're gonna do that with finals. Oh, Santino, that's right. Yeah, I'm not sure how we're gonna do that or not. Yeah, there's a chance we might not. But I'm gonna have a department meeting tomorrow with the other science teachers, and we'll probably maybe decide on something tomorrow. If not, we'll keep you updated. But at the moment, it seems like we're kind of leaning towards maybe not having finals, or if we do, it'd be way shorter and than usual or simpler than usual. But I'm not too sure yet. Yeah, hopefully I'll find out more information tomorrow though. Yeah, if you guys do have any questions, just let me know. If you want to go over any Hess's law problems or entropy questions or heat equation questions or anything like that, we can definitely go through that stuff.
Yeah, let me know if you guys have any questions about anything. I'd be more than happy to go through it with you guys. Hope you guys are doing well. Just let me know if you have any questions about anything you want to go through. Entropy questions, Hess's law, heat equation questions, or examples. Anything at all, we can go through it if you guys want. For the entropy questions, the one that's spontaneous is the sugar dissolving in the water. So I think that was A. B is talking about building a brick wall, right? Let me double check. Yeah, A is spontaneous because A is sugar dissolving in water. A sugar cube placed in water is automatically just going to disperse itself into multiple different possible locations and states. But a pile of bricks changing into a brick wall is not spontaneous. You have to actually make that happen. Like if you have a pile of bricks just sitting there, they're not going to become a wall. But if you have a sugar cube sitting in a thing of water, it's going to disperse. So yeah, it would be A. A would be the one, yeah. So if the sugar cube just sitting in water, it's going to automatically disperse itself. Ow. But if you have a pile of bricks just lying on the ground, they're not going to automatically build themselves into like a wall. Yeah, pretty much everything's weighted the same, yeah. Yeah, if you guys want to go over any other questions or anything, I'd be more than happy to go through some with you guys. Just let me know what you guys want to go through. Number one, let me double check what that was. So for number one, it's going to be basically the state at a higher temperature, right? Because like, here, let me show you. Because I know the only heating curve we've ever seen is the one for water, but it's pretty much analogous with the other compounds out there. With any other compound, it's pretty much analogous. So temperature is the y-axis, heat is the x-axis. It's been a while, but we did see this. Well, actually, it shouldn't have been that long ago. It was on the worksheet for the phase change. But we also saw this on when we were looking at liquids earlier before we left for this whole pandemic stuff going on. But solids always exist at a lower temperature. That's the y-axis. Liquids are at higher temperatures, and gases are at higher temperatures, right? Because if you're adding heat, Q is heat, right? So if you're increasing the heat, which is Q, it's going to raise the temperature. So a gas is much more spontaneous than a liquid. So for A, 1 gram of steam is more entropic, it's more entropy. And for B, 1 gram of iodine vapor has more entropy. So yeah, what you said is correct. Yeah, what you said is fine. Because yeah, if it's a gas, it doesn't just have an unfixed shape, but it has an unfixed volume, right? Liquids, for the most part, have a fixed volume. You can, under some circumstances, slightly change their volume, but for the most part, liquids have a fixed volume. Gases have an unfixed volume. They like to maximize their volume, if anything. So there's so many different possible combinations of different places, locations, and states these gas particles could be in. So yeah, so what you said is correct. Yeah, delta S is change in entropy. So entropy is the letter S. Not sure why it's the letter S. Maybe it's for spontaneous. I'm not sure. Yeah, it's the letter S. Yeah, for number two, they're both positive entropy, exactly, because they're both going to gases, or yeah, one's going to gas and the other one's just increasing in temperature. So yeah, that's definitely the case. And that's something that might potentially get confusing. No one's brought it up before, so I don't know, maybe I shouldn't mention it, but I kind of feel like it'd be nice to mention it. But entropy, right? Change in entropy has the units joules per Kelvin. So we've already talked about those units, joules per Kelvin, right? So that's basically heat per temperature, right? So the units for entropy are joules per Kelvin, which is heat per temperature or energy per temperature. Yet, if these things are at higher temperatures, they have more entropy, which almost seems counterintuitive because that's on the denominator, right? But it kind of goes hand in hand because if they're going to be at higher temperatures, they're moving faster, so they have more kinetic energy automatically, so their heat value is already larger. This might not necessarily, it's probably best instead of put heat here to put enthalpy, the internal energy of the substance, really. Because yeah, the units for entropy are joules per Kelvin, which is like the enthalpy, the internal energy per temperature. And yeah, if it's at a higher temperature, it has more possible states. It's more random. It's more disorderly. So it's more has a higher entropy. It's more entropic, and that's kind of almost counterintuitive because it is on the denominator. But by definition, because they're moving at higher velocities, higher kinetic energy, which is what temperature is, a measure of kinetic energy, they're going to have more enthalpy. There's going to be more energy within the whole thing altogether. So yeah, if something's increasing in temperature, it's pretty much going to be more entropy because it's going to be moving faster. It could just be in more possible locations. I just think about it like disorder and randomness, right? Because think of water as an example. An ice cube is frozen H2O, and there is movement there. They're vibrating, they're shaking within the cube, but they're not moving translationally. They're not going from point A to point B. They're not like traveling. They're just sitting in their own location, shaking, right? But if you add heat to that, which raises the temperature, and it's a liquid, they can move around actually. They can change their location. So there's more possible randomness. There's more disorder of where they could be. And if you add even more heat to that, the temperature goes above 100 degrees if it's water, right? If it's really high, like past 100, it's going to be a gas. It's going to be steam. So that maximizes its volume, and it's going to be in so many random different locations, right? So it's even more disorderly, even more random. So yeah, if it's going to increase in temperature, it's going to increase in entropy for sure. Yeah, let me know if you guys have any other questions or anything. If you want to look at any Hess's law or other entropy questions. Entropy can be kind of confusing at first, so it just kind of takes some getting used to think about. But yeah, it's really the second law of thermodynamics, which we weren't really looking at exclusively or explicitly. Um, the first law we already know about. It's pretty similar to conservation of mass, but it's talking about energy. So energy can never be created nor destroyed, just transferred from one form to another. That's the first law. The second law is really all about entropy. The second law says that any closed, isolated system will have an increase in entropy. So, for example, we consider like that ice cube, for example, if it's closed or an isolated system, if you're not allowed to add more energy into it, like putting it in a freezer by adding electrical energy and doing work on it, if it's just sitting out in the open, it's going to basically have an increase in entropy. So yeah, the total entropy of an isolated or closed system can never go down. That's the second law. And it's kind of weird because technically the second law of thermodynamics and entropy itself predicts how the universe will end too, right? Because we know that heat goes from hot objects to cooler objects, right? If my hands are by a fire, the heat's going from the flames to my hands, right? So it goes from hot to cold objects. And that happens obviously on these large astronomical scales too, like stars and entire galaxies, right? There's lots of empty space in between galaxies. But galaxies themselves and stars themselves, they transfer heat from hotter objects to cooler objects all the time. And eventually that's going to keep happening until everything's the same temperature, right? Because if I'm holding something cold in my hand is hotter, and whatever thing I'm holding is colder, like a cold piece of fruit or something, eventually that cold piece of fruit's going to be the same temperature as my hand, right? Heat's going to go from my hotter hand to the colder piece of fruit until they're both the same temperature. So all these large stars and astronomical bodies are going to be passing heat from hotter objects to colder objects until they're all the same temperature. Now the universe, as far as we know, right? There's so many theories out there, but as far as we know, the universe is a closed system. The universe is everything, right? There isn't like extra space beyond the universe. It's just the universe, right? It's just the universe. There's nothing like extra that is like the universe number 2 or whatever. Like it's all a closed system. So because it's a closed system, you're not going to be able to add extra work into that system. You can't just magically drop some extra energy into there. So it predicts that there's going to be this heat death of the universe eventually, where everything's going to be done transferring heat from hotter objects to colder objects. So eventually everything's the same temperature. And it doesn't mean everything's going to be hot. It's called the heat death of the universe, but really everything's going to be probably more likely cold, because the hotter objects are going to go down in temperature. They're going to give the cooler objects a raise in temperature, but everything's going to be the same. Everything's going to level out. So yeah, that's the most likely proposed theory for the end of the universe, is this heat death theory, which entropy pretty much explains exactly, and so does the second law of thermodynamics. Because entropy really explains why heat goes from hot to cold objects anyways, right? Because if there's a hotter object, it has its particles moving much faster at higher velocities. There's more enthalpy, there's more heat content. It's probably at a higher temperature. So if it's placed next to a cold object, which has particles that aren't moving that much, it's more likely to transfer heat to them and cause them to move a little bit more, and the hotter object particles to move a little bit less, and so they're both moving about the same speed, so they're the same temperature. Right? So entropy really explains why heat goes from hot to cold objects. Yeah, let me know if you guys have any other questions at all, though. Yeah, I seriously doubt that. Um, Yeah, I don't know. Because if there was some sort of, you know, sentient being out, some sort of like beings that are maybe from another planet or another galaxy that were like around during that time, they would probably go extinct during that whole heat transfer period because there would be such a decrease in their planet's temperature, or maybe such an increase in their planet's temperature, that they would have to adapt way too quickly, and they might just go extinct anyways. So I'm not sure, but yeah, probably not. That's my best guess, but I'm not sure though. Oh, the test next week? I think it's shorter than the last one. It's not too long. Um, there's some multiple choice questions. There's one Hess's Law question. Yeah, just like one Hess's Law question, it looks like. Um, yeah, there's not that much. There's only like 12 questions, I think. I kept it relatively short, just 'cause I feel like the other one was a bit too long, maybe. So it was a little bit short. Yeah, so it's definitely shorter than the last one. Yeah, let me know if you guys have any other questions at all. If you need any help with anything else. A Hess's law problem? Yeah. So, let's see. I'll try to look for one real quick. Okay, let's try this one out. So, all right, so we have this one here. Let's see. So we're trying to get the equation on top, right? So phosphorus trichloride plus chlorine gives us phosphorus pentachloride. And so we have two equations down the bottom. We have, how many is that? 2? 2 moles of phosphorus plus 3 moles of chlorine gives us 5 moles of phosphorus trichloride. Then we have 2 moles of phosphorus plus 2 moles of chlorine gives us 2 moles of phosphorus dichloride. So we want to try to build the thing on top, right? So first thing is we want phosphorus trichloride on the left, right? We want 1 mole of it, and we want 1 mole of it on the left. So there's no phosphorus trichloride here, but there is in the first one, right? The first one has phosphorus trichloride right over here on the product side. So it's on the wrong side. I want it as a reactant, and I have it as a product here. So I'm going to have to use a negative sign, right? Switch them because it's on the wrong side. It's a product here, but I need it as a reactant. And then it's also the wrong amount. I have 2 here, but I need 1. All right, so since I have 2 moles of it here, but I need 1 mole of it over here, it's on the wrong side, so it's going to be a negative. I'm trying to turn that 2 into a 1. So I'm probably going to have to multiply by 1/2. Right, so I'm going to multiply that by negative 1/2. Right, that'll help me with that part so far. Negative 1/2. It's kind of hard to see, but we'll try our best. Let's see if we put it here. Okay. And all right, so we're gonna multiply the first one by negative 1/2. That way we can flip the products and the reactants, and I can turn that 2 from phosphorus trichloride into a 1. Other than that, I want 1 mole of chlorine on the left. I have 3 moles of chlorine here on the left, but it's gonna get flipped, right? Because I'm gonna multiply it by negative 1/2. So it's really gonna be 3 moles on the right. Okay, and then I have 2 moles of chlorine on the left over here. All right, so I have 2 moles of chlorine over here, and I'm going to have 3 over 2, because it's going to be divided by 1/2, 3 over 2 over here on the right. So that might take care of it, because I have 2 moles of chlorine over here, right? And then I'm going to have 3 over 2 moles of chlorine over here. That's 1/2. 2 minus 1/2 is only half chlorine. I need 1 mole of chlorine. So I'm not quite there yet. So we'll see what we need to do next. For this one, though, let's see. I also need 1 mole of phosphorus dichloride on the right side. I don't have it here, but I have it down here. I have 2 moles of phosphorus dichloride on the right. I need 1 mole of phosphorus dichloride on the right. So it's on the correct side, right? They're both on the product side, but I need this 2 to become a 1. So I'm going to multiply this one probably by positive 1/2. All right, let's try to multiply it by positive 1/2. All right, so I'm going to multiply the first one by negative 1/2. I'll multiply the second one by positive 1/2. So let me go ahead and get that started and see what we'll get. So negative 640 over 2, so negative 320, or positive 320 really. And then that's going to multiply by 1/2, so it's going to be P, 5 over 2, P plus 5 over 2, PCl3. PCl2, I should say. Or Cl2, it's just Cl2. Five PCl, and then 1 PCl5. PCl3, I should say. Oh no, it is a 5. Yeah, it's a 5. Just double check here. Okay, so it's just hard writing on both sides because it kind of messes things up. All right, so that was PCl3. Okay, so, all right, so again, just to remind you, for the first one, I multiplied it by negative 1/2 because I need PCl3, right? I need PCl3 on the left side. I need to turn that 2 into a 1. So that's why I multiplied it by negative 1/2 to make it go to the other side and to make the 2 become a 1. So I can have it as 1 PCl3 on the left. For this one, I just multiplied it by positive 1/2 because I want PCl5, that's a 5, I think I was calling it a 2, PCl5, I want that on the right-hand side. So like over here, I have PCl5. I might have been calling it di instead of penta because it looks like a 2 on my end. So I want PCl5 on the right-hand side, but I only want 1 mole of it, not 2. So I'm multiplying it by 1/2 just to get that done. So I have this after I made those changes. All right, so again, for the first one, I multiplied it by negative 1/2. So the products and reactants are going to flip for the first one and multiplied by 1/2. So I went from 2P to 1P on the right. I went from 3Cl2 on the left to 3 over 2 Cl2 on the right. And I went from 2 PCl3 on the right to just PCl3 on the left. All right, for the next one, I multiplied it by 1/2. So all those factors are going to get divided by 2, but they're going to stay on the same side, luckily. So I went from 2P on the left to 1P on the left. I went from 5 Cl2 on the left to 5 over 2 Cl2 on the left. And I went from 2 PCl5 on the right to just 1 PCl5 on the right. Okay, so again, I'm trying to get this thing up here in the box. I want 1 PCl3 on the left and 1 Cl2 on the left. So let's try those. 1 PCl3 on the left and 1 Cl2 on the left. So do I have any of those? Let's see. I want 1 PCl, I think I was saying 2. Sorry, I keep getting my words mixed up. I want 1 PCl3 on the left and 1 Cl2 on the left. So PCl3 and Cl2. So I've got PCl3 on the left, and it's 1. That's perfect. I want that. And I want 1 Cl2 on the left. This is where it gets kind of tricky because I have 5 over 2 Cl2 on the left, and I have 3 over 2 Cl2 on the right. So it's the same substance, right? It's chlorine, it's Cl2, it's the same substance, but I have 5 over 2 here and 3 over 2 there. So they're on opposite sides, so we're just going to have to subtract, right? And they have a common denominator, 2 and 2. So you just do 5 minus 3. You just subtract the numerator. So 5 minus 3 is 2. So that gives us 2 over 2, right? Because you keep the common denominator. 5 minus 3 is 2. They're still over 2. So you get 2 over 2, which is 1 Cl2. So basically, this guy's going to cancel. This guy's going to cancel, and this is going to become 1 Cl2, right? Because I did 5 over 2 minus 3 over 2, which is 1. That's just 2 over 2, right? So 2 over 2 is 1, and that's perfect because I want 1 Cl2 on the left. So I have 1 PCl3 on the left and 1 Cl2 on the left so far, and that's what I want, so that's good. And I want 1 PCl5 on the right-hand side, all right? So I got that. I have 1 PCl5 on the right, so we're good to go. However, I have some extra stuff here, right? I have 1 mole of phosphorus on the right, 1 mole of phosphorus on the left. It's the same substance, but they're on opposite sides, so they're going to subtract. So 1 minus 1, so they basically just cancel out. So what we have left is PCl3 plus Cl2 produces PCl5. So I got exactly what I wanted. PCl3 plus Cl2 goes to PCl5. Right, because that's what's left over, 1 PCl3, 1 Cl2, because I did 5 over 2 minus 3 over 2, so that's 1 Cl2. That's 2 over 2, which is 1. And I get 1 PCl5 on the right. Okay, so now I just got to add up my enthalpies. So I already multiplied them by those numbers. I multiplied the first one by negative 1/2, and I got positive 320. Is that 320? Yeah, 320. I multiplied the second one by 1/2, and so I got negative 446 because it was originally 880. 443 because it was originally 886. It was negative 886. So now I have negative 443. So my final answer is putting those together. So 320 minus 443, whatever that is. 320 minus 443. So my final answer is negative 123 kilojoules. So yeah, my final answer is negative 123 kilojoules. Let me know if you have any questions about this one at all. It does get kind of tricky if there's fractions involved because sometimes people forget about how to subtract fractions or add fractions. Just remember they have to have a common denominator. In this case, it worked out. They already did. They both had a 2 on the bottom. So then it's just 5 over 2 minus 3 over 2. So you keep the 2 on the bottom. So it's just 5 minus 3, which is 2. So you have 2 over 2, which is 1. That's why I got 1 Cl2 here. You might have already remembered that, but some people forget how to subtract fractions, so that could be kind of tricky. It's they learned it like maybe 5th grade, so it's been a while. But yeah. But let me know if you have any questions about this one at all, or if you want to see any other examples at all. I might add one more video of notes, actually, just to explain how these things tie in with the laws of thermodynamics. So I feel like the notes we already have weren't very directly referencing the laws of thermodynamics enough. So I'm going to make one more video of notes. It'll be a quick explanation. It won't be something that'll be like super huge on the test or anything, but just one more video of notes just to kind of see how it all ties in together. Yeah, let me know if you have any other questions or anything. In fact, wait one moment. I'll be right back. Just one, if you have any questions. All right, so yeah, let me know if you have any other questions or anything. Oh, nice. I feel like that was one we did the other day, the first one. Oh, did you see? I don't know if did you see the one I just did too? I might have looked at your question a little bit late, but I just did a problem. We can do that one though if you want. I'm down to do that one. One moment. All right, so let's take a look at that one then. Okay, cool. I just wanted to make sure. I might have gotten to your question late because I didn't see it. I had to scroll down, I guess. So we're trying to get that one. We have those other two things. Is that all together? I feel like. Oh, okay. So there's 3 steps to it. Okay. There's 3 steps. But I'm trying to find where the C2H2 is. I don't see that anywhere. I feel like they're missing C2H2. But it has 6 equations. We could try it. It might be kind of hard to fit on the board. It might get kind of intense. But yeah, we can try it out. But yeah, it'll probably just stick to 2 equations on the test. Yeah, if you want to, we can try it. It might just be might take me a while to go through. It might be kind of hard to fit on the whiteboard, but we can try it out. Yeah, just let me know if you have any questions or anything. If you want to, we could try it. Might just take a little while. We could try it if you want to. If you have all the other ones, or if you want, you can send me a link to like the page you're on in case it takes forever for you to type it all out. You said there's 6 equations, so there's probably like what, 2 more to type out. You can just send me a link if you want, because it might take you a while to type it all out. I thought you said you had 6 equations. I only see 1, 2, 3 plus the target one. So you have the target one, and you have 3 more after that. It's just because I don't see the C2H2, so I think that's missing. Yeah, the carbon's there, the hydrogen's there, but I don't see the C2H2. It looks like something's still missing. Yeah, I only see. Here, I'll show you what I see. I see this. I see that. I see this. And I see this. I feel like I don't see the C2H2 anywhere in the sample equations to manipulate. Unless there's like a lag or something on the live stream, maybe I'm just not seeing it. So those are the only ones I see. Yeah, I got that one already. Yeah, I have that one. I just don't see the one that has C2H2 on it. Don't see it anywhere. Oh, the ones that I just typed in and sent you, those are the only ones I see. The one you just sent me is the last one I just typed out. But none of them have C2H2. I'm looking for that thing. I don't see it anywhere. I see it in the target equation, but I don't see it in the ones below it. Yeah. Yeah, I don't see C2H2 anywhere still. I'll go back up in case I miss it, but I don't. Yeah, I don't see it. Which one's example 5? You have a link to the page? Yeah, I don't see example 5. No, I didn't get a link. Try sending it again. I didn't get it. Yeah, I didn't get a link. Try to see if you can send it again. Yes, I still didn't get the link. You can still go through it if you'd like to, but I didn't get it still. Yeah, I still haven't gotten it. It's really weird. I have all the equations you typed up, but I don't have your link. You're sending it to the live chat, right? Not like somewhere else. I don't have the link at all. Maybe here. Maybe send it there. Just send it to my email or something. Yeah, I haven't gotten it at all. All right, cool. I'll check that out. So I got that. Let's see. All right, so you said it's example 5? Wait, which one did you say? Example 5? Okay, cool. Example 5. Oh, that's a long one. Yeah, so let's see. We're trying to get here. For the sake of ease, let's just keep this thing down here. So I'll just keep that there. That's the target reaction. And we'll just work on the board with the other ones because it might take a while. So, all right, let's see. A lot of things here. Calcium oxide plus water produces calcium hydroxide. Delta H. I'm just going to leave off the units just because this is already going to take up a lot of space. I'm just going to put the number down. And then 2 moles of calcium oxide plus 5 moles of carbon. This one's long. Excuse me. Gives us 2 moles of calcium carbonate. Plus carbon dioxide. That H is 753. I might not even put the deltas. I'll just call them H just because of how crowded it is. We have calcium carbonate, produces calcium oxide plus carbon dioxide, and that H is 178. We have calcium dicarbonate plus 2 moles of water gives us calcium hydroxide and C2H2. And then that is negative 126. That's the first negative one, right? No, the first one was negative 2. Okay. Then we have carbon plus oxygen gives us carbon dioxide, and that H is negative 393.5. And then we have 2 moles of water produces 2 moles of hydrogen plus 1 mole of oxygen. And that H is 572. Okay, so it's quite a doozy. Let's see though. So first of all, hey Isaac, how's it going? We're doing a Hess's Law problem right now, but it's pretty insane, just to give you a heads up. This one has 6 equations to work with. We're never going to do one this crazy. We're just going to do ones that have like 2 equations to work with for the test. So just, I'm going to put this on the board, but just don't let it, I'm going to put this on the screen, but don't let it freak you out. So this is 572. I should just leave this open. All right, so 572. All right, so these are all 6. So like I said, Isaac, we won't do one this crazy because I know you just got in here right now. Our Hess's Law problems is going to be like 2 equations. This is 6. This is like a crazy one. So I want 2 moles of carbon on the left. All right, there's no carbon on the first one. There's 5 moles of carbon on the second one. Okay, I'll keep my eye on the second one. There's none here on the third one. There's none on the fourth one. And there's 1 mole of carbon on the left on the fifth one. So just the second and fifth one. All right, so they're on the same side. So that means they're going to add to 7. But I don't want 7. I just want 2. So I'm probably going to have to do something about that. All right, now let's just take this one step at a time, because there's lots of stuff here that I want to cancel too. I also want 1 mole of hydrogen on the left. Hydrogen is only on the bottom one. It's on the right side, and there's 2 moles, and I want 1 mole. I don't see any other hydrogen, so I'm going to multiply the bottom one by negative 1/2 to have it switch sides, and to divide by 2. So far I just have one thing planned out, right? So I'm going to multiply the last one by negative 1/2 to have the hydrogen on the left side and to have only 1 of it, not 2 of it. All right, so far, making baby steps. And then I want 1 mole of C2H2 on the right. I've already got that here. So I'm good to go there. So all the work I'm going to be doing here is literally just going to be getting things to cancel, it looks like. So that's literally what all this is going to be, just getting things to cancel. So let's see what I should do. I kind of need to look at it for a while first. So I don't want calcium hydroxide at all. So I should probably multiply the first one by negative 1. Okay, that'll fix a couple things for me. So I'm going to multiply the first one by negative 1 to get my calcium hydroxides to cancel. It's hard to fit where I'm going to write all this stuff. So you know what? I'm going to get rid of all the H values. I'll just look them back up later because there's just no room. So I'm going to get rid of all the H values here. I should get like a big whiteboard. I just don't know where I'd put it. Get rid of all the H values. Now let's see. I'm going to multiply the last one by negative 1/2. We already established that. I'll multiply the first one by negative 1. So I got rid of all the H values just to make some room. So yeah, like I said, Isaac, don't worry about this one. It's kind of crazy. So I'm going to multiply this one by -1/2 to get the H2 on the left side and make it go from 2 moles to 1 mole. I'll multiply the first one by -1 just so I can get the calcium hydroxides to cancel. And that'll probably also help me cancel those waters too. Because if I multiply the first one by -1, hopefully you're kind of following along with the web page, Ryan, because I'm going to be looking at this a lot, so it's going to be hard for me to like show it to you the whole time. So just keep that in mind. So if I multiply the first one by -1, I'll get my calcium hydroxides to cancel, the CaOH2s, and it'll probably help me cancel the waters as well. Because I have 2 moles of water. Yeah, check that out. So I'm going to flip this guy. I'm going to flip the first one. And I have 2 moles of water on the left here, right? That's 2 moles of water on the left. This is going to be 1 mole of water on the right. And there's already, wasn't there another water? Well, I'm already going to get those waters to cancel. So I'm going to have another water up there, which I don't want to be there. Let me see. This might take a little while. So if I multiply that one by 2, let me double check something real quick. So we might not need all of these reactions. It looks like, yeah, because the one of calcium carbonate, we don't need calcium carbonate, and it doesn't even come up anywhere. So I'm going to erase the third one. The third one's just extra. We don't need that because calcium carbonate, we can't even cancel it if we wanted to. There's no other calcium carbonate anywhere for it to cancel. So the third one's just extra information we didn't need. So it's really just these 5. Right? So it's just these 5. The third one went away because there was no way for us to cancel the calcium carbonate anyways. And that helps us out a little bit because now the calcium hydroxides are going to cancel for sure. The calcium oxides I want to have cancel. So I'm probably going to have to do a couple of other things. 5 plus that one's 6. I don't want there. I want that to be 2. Maybe I should multiply the second one by -1/2. Sure, I'm just going to do some things. -1/2. Let's try that. Let's multiply this one by 1/2. We'll have 5/2 carbons and 1/2 carbons. But that's still, oh, that will help me. Okay, that's good. Now I'm not sure about the waters. And the calcium oxide, there's no other calcium, oh no, there is, okay. Okay, so sort of making some progress. All right, so I'm gonna multiply this one by -1, that one by -1/2, and this one by +1/2. And we'll see what happens. We're just taking baby steps at a time. So I'll flip that one around. So calcium hydroxide. CaO and H2O. Calcium oxide and water. That one's going to be flipped around -2, so that'll be CaCa2, CaC2, CaC2, and half CO2 plus 1/2 CO2. I think I'm making some progress here, hopefully. Then CaO and then 5/2C. CaO plus 5/2C. CaO 5/2C, okay. I'll keep that one the way it is. So it's going to be CaOH2, CaOH2, and C2H2. Next one, I'll multiply by half, so it's going to be half C plus half O2 goes to half CO2. And then that one will flip around, so it's going to be H2 plus half O2. Hopefully this starts to fall in place. And then H2O is over there. Okay, so again, I multiplied the first one by -1, multiply the second one by -1/2, multiply the, used to be the fifth one, but now it's the fourth one, by half, and I multiplied the last one by -1/2, because again, I skipped the third one, it was unnecessary. So now I have all this. All right, so let's see what we get. So calcium hydroxide luckily cancels. I have a couple of other things here. Maybe I wasn't supposed to flip around that one. Oh, you know what? Yeah, I wasn't supposed to flip around that one. This is going to take me a while. So here, let me go back. Let's just call that +1/2, and let's flip around this one. Let's call this one -1/2. All right, so I'm going to slight change. I'm going to multiply the second one by just +1/2 and the last one by -1/2. So this was positive, this was negative, but now I just flipped them. All right, so let's see. So I'm getting lost. So now it's just going to be CaO right there. CaO, it's not negative anymore, plus 5/2C, plus 5/2C. And then that's going to be CaC2. That's going to be half CO2. And this one is now going to flip. So now for this one, I'm going to have half CO2 on the left. Okay, this is looking a lot better. Okay. And then I'm going to have half C plus half O2 on the right. All right, so just to remind you, I multiplied the first one by -1, the second one by +1/2. This one went away, nothing to that one. This one I multiplied by -1/2, and this one I multiplied by -1/2 as well. Did I finish doing everything? Yeah, I finished doing everything. Double checking. Yeah, okay. So this is what I have left over. So my calcium hydroxides are going to cancel. All right, so this is what I have. I think I should have done on side. I did all of this stuff, right? So -1/2, +1, -1, +1/2. This one went away. This one's nothing. -1/2 and -1/2. So I have this stuff right now. My calcium hydroxides canceled. I already showed that. My calcium oxides can now cancel. My calcium dicarbonates can cancel. My water is going to cancel too, thankfully, right? Because I have H2O here as a product and H2O there as a product. So that's 2, right? 1 plus 1. And there's 2 H2O there. So all my waters are going to be gone. They're all going to cancel. So I have 2 as a reactant and 2 as a product. All right, we're making some progress. Now, my half O2s are going to cancel. Oh, this is getting beautiful now. Thank God. My half CO2s are going to cancel. Okay, I finally finished it. All right, so we're about to finish. Everything basically canceled. So I have 5/2 C's here. That's 2.5, right? And I have 1/2 C's here. That's half. So 2.5 minus half is 2, right? So I'm going to get 2 C's on the reactants. So I have 2 C's on the reactants. That other one went away because we subtracted it. Plus H2 on the reactant, and then C2H2 as a product. We finally got it, right? So we finally got it. We got 2C plus H2 goes to C2H2. It just took forever. It was just a lot of canceling. So again, just to remind you, what we did was we multiplied the first one by -1, multiplied the second one by +1/2. The third one, just erase it. It was just a trick part of the question. This one we didn't do anything to. This one we multiplied by -1/2, and this one multiplied by -1/2. So the final answer, I don't really feel like doing it. The final answer is just put all that stuff together, right? So it's -1 times whatever the first one was. So yeah, -1. So it's going to be 65.3 plus half of 753. You don't need the third one, so that's not going to be in there. Plus -126 plus whatever -0.5 is times -393.5 plus whatever -0.5 is by 572 kilojoules. It looks like they probably show it too. Yeah, they show you the answer on there too. So it looks like the answer is 226.55 kilojoules. It just took a while to get everything to cancel. But yeah, so yeah, that was kind of a doozy. We did all that stuff. Those are all the factors we multiplied them by. That one went away. Nothing. -1/2, -1/2, -1/2, nothing. Stayed the same. -1/2, -1/2. And that's how everything canceled. So yeah, that one was crazy. That one was pretty crazy. It's kind of satisfying and fun once everything starts to cancel, though. It's a nice feeling. Yeah, let me know if you have any other questions. That'd be like an AP level problem, probably. Or I don't know, if we were actually doing this stuff in class in person, I had a better effective way of like getting to teach you guys because I'm not just online. I might have made something like that a bonus question, but I wouldn't even make that a bonus question now because I don't want to give people headaches. So yeah, it's just a crazy one. Yeah, I might probably get going unless you have any other questions. I've been going for a little while. But I'm going to probably add a little bit more, one more video of notes for tomorrow just to kind of summarize how everything goes together with the laws of thermodynamics. So I'll probably do that right now. Yeah, do you have any other last minute questions? I'll probably get going in a minute. Ooh. Oh, no. Oh, I almost accidentally ended it. Yeah, I guess technically, I mean, because I multiplied them by like, half, 1, -1/2, -1/2. I guess you can. It would just be that's the simplest way is the way I did it. But you could just, for example, multiply everything by a factor of 2 or a factor of 4. So instead of 1, it'd be 2. Instead of 1/2, it'd be 1. Instead of -1/2, it'd be -1. Instead of -1/2, it'd be -1 again. So it just if you have like a bigger factor, a larger factor, or something, yeah. I just did it like the simplest way. But I guess you could do it other ways. You'd still get the same number, the same result. It would just be larger factors, I guess. Yeah, I might get going a little bit. I might go use the restroom in a second. But yeah, I'll add one more video for tomorrow, just a quick one, just to kind of summarize the laws of thermodynamics of everything. But there's no quiz tomorrow or anything. It's just some notes. That's basically it. Yeah, this one was pretty long. Yeah, That one took a little while, but it was fun. That was a fun one to do. Yeah, but I'll probably get going unless you have any other last minute questions or anything. All right, for sure. Well, hope you have a nice rest of your day. Take it easy. Have a good one.